I'm going to discuss about Singularity Apptainer. So this is a bit, in a way, a continuation, even there's not that much direct link in a way, of the previous talk. So there's some functionality that you can use actually for continuous deployment of your software that you can also use, of course, within your CI/CD to basically have something that can run on different clusters, that you can do one installations in a way, and then you can run in different places. So that's something very useful. So Singularity Apptainer, for those who don't know, in one word, is a container solutions, and it's a container solutions for HPC. I will come back. Singularity is kind of the old name or the proprietary name in a way, and Apptainer is a new name for a version which is actually not yet released, we're still in beta. So what I want to cover during this talk is first, what is a container and what is used for, and therefore why is it interesting for you, how this can help, and I already give some solutions in a way in that directions. Then I will move on more in details why to use Singularity and not use for another container solutions, which is of course, for example, Docker, and why Singularity is the solutions for doing container on HPC infrastructures and why Docker is not actually. During this talk, I will do a couple of demonstrations to show you that basically everything is relatively easy. I would say it's a bit more complex probably than the CI/CD, where everything in a way was done for you. And of course, how to use those containers on HPC, and that means how to use the specificity of HPC, that in particular the InfiniBand, the GPU, and so on and so on. One of the main reasons to go to container is to have one of the answers, let's say, of this huge problem of installing and deploying software. I'm personally a physicist actually, and also an IT here in university, system administrator at my university. And in both cases, I need to handle the issue of installing software. And therefore, I know both as user, but also as system administrator, how it can be difficult to have a fully automated procedures to install your software. The main reason is, of course, that your software, you don't want to invent the wheel, and that makes perfect sense. You don't want to say that you are going to recode everything, otherwise it typically will not be done correctly. You want to use the code done by someone else, and they've done some of them fantastic jobs, obviously, and completely optimized, and that's the way to go, is to use the code of someone else. But therefore, your code, which is maybe relatively easy in itself, has now dependencies, and that code itself is using the code of someone else, so it has a lot of dependencies going in all directions, as you can see in here, right? What you are interested in is these jobs, which contains something like 15 dependencies, and itself they all have dependencies, and then you need to be installing all those code in the correct order. And if you do that, you typically do a /configure, then you realize, oh, I'm missing that dependency, then you're installing it, and then you realize, and so on, and you can take a lot of time. And this is a big issue in a way, and that's why there's solutions that we've here before, SPAC, EasyBuild, but also in a way a lot of other tools like Configure, Auto Tools and stuff like that, which are in a way trying to help in that direction. So this is a cartoon that they've stolen from Kenneth Ost, which is one of the main author, if not the main author of EasyBuild actually. It's how to become invaluable, and just by knowing how to install the software actually, and that is represent actually a lot of value. So one solution here is a container. So a container is really kind of a small machine. So it contains a small OS. It contains, of course, your code, but it also contains all the dependencies. So it's really something that is self-consistent in a way. And that's the main idea of container, that it can actually be shipped. And therefore, it's kind of also standardized, sorry for my probably bad English. And it can ship. It can be run on HPC infrastructures, that's our main goal in a way, but also on your laptop on plenty of different places, on different clusters as well. So that's really this idea of container, to have something with relatively clear boundary, really clearly well done, so that you can be run everywhere. So this is actually a quite old idea. I mean, this idea of container go back actually up to the late of the 80s, so it's actually quite old. It's really starting to grow, I would say, with Docker. And Docker, its main principle is really also to isolate. So you want to isolate your container from the rest of the system, which is perfect actually for cloud computing. But the issue is that this doesn't work very well with multi-user environment, with resource like interconnect, GPU, and stuff like that, where you actually, if you have multiple users, you have some resource that you are the right to use, you have some quota and stuff like that, and that doesn't work very well with Docker. So they try actually to move Docker and HPC, and basically was not working, and therefore another group started in 2016, what is called Singularity, and which is really designed for HPC. And by that, the philosophy is actually completely different. So instead of isolating your process and being root inside the process, they actually integrate your container within the HPC environment. So that means, and you will see that later, it's really designed for multi-user, and therefore within the container, everything that you run within the container is with the same right access that outside the container. And that is a completely different philosophy compared to Docker. And that's the main point, I would say, of Singularity, is really integrate the container with your environment rather than isolating it. And therefore you have access to basically every advanced hardware exactly as if you are running directly on the cluster. So now Singularity are kind of split in two. So there's Singularity and Apptainer, which Apptainer is going to be released. It's in beta for the moment. They kind of diverge from the same code. So if you look at Apptainer, they say that's basically they have a continuation of Singularity. The main reason is that Singularity is now mainly developed and handled by Syslab, which is a private company. And therefore, even if the Singularity itself, the code was actually open source, and therefore they now are moving, Apptainer at least is moving to the Linux foundations, and therefore kind of far from Singularity. So now you have those two codes, which is not yet fully clear, at least for me, how those two codes will move forwards together or not together. So Apptainer actually has removed a lot of private API related to the Singularity cloud, and I will discuss that later. But they're also introducing new features, like, for example, checkpointing with the MTCP, so the talk of yesterday. So it's not clear how Singularity itself is going to take those features or not. That dynamic is not yet settled, I would say. We'll see that in the future. In any case, what I will present today is only Singularity itself, to be clear. So I'm going to use those private API, actually, which I think are very nice and really nice to use. But okay, that is a bit politics in a way. So for now, we have Singularity. Apptainer is coming with great new features, to be honest. We'll see if they will be also incorporated in the Syslab related environment. So what are you going to use container and Singularity for? And this is maybe a bit more for scientists in a way, but for me there is two stuff, obviously. The first one is reproducibility. So how to be able to send your code to a collaborator, to your supervisor, to a colleague or whatever, and be able to use the code out of the box. That means without having this issue that you have to basically set up for weeks or even more in some cases, all those library, all those dependency on these machines, and be sure that basically you do that, you run, you edit that file if you want to do something, but you basically have a code which is running out of the box. So that's for me a big stuff. To basically being able for a colleague to check your code, for a colleague to continue what you are working in a way, or whatever. So I think it's really a nice way to collaborate. So that's something I would say it's in the same directions for reproducibility at the end of the day. What is the most important to reproduce for me is the result of a paper. And therefore, providing a Singularity container or a container in general here, to be having people to be able to reproduce the results in your paper is of course, I think, something very nice. I'm always referring myself. A couple of years ago, there was a huge experimental discovery for gravitational wave in physics. And that one was they were providing basically the full code. And you say, if you want to check a result, is the code source, is the data, you run them and you can basically reproduce a result. And you can, of course, look at everything, change whatever you want. And that, of course, makes myself, if I don't know anything in that particular part of physics, makes me quite confident about their result. And of course, what I put here, the second point, deployment, that's what is CI/CD is about, what we discussed before. If you need to test your code on a lot of infrastructures, you need to be able to deploy it. And therefore, you need to have an easy way to deploy your code. If you need to be on Ubuntu, an easy way to run Ubuntu, you're on cluster, which typically are on CentOS, and so on, and so on, and so on. So, and of course, if you have something which is easy to deploy, that means you can run easily in a lot of places, and that's of course an advantage for you at the end of the day. One typical other solutions, I would say, is the virtual machines. So you can actually also say, oh, I'm going to install everything in the virtual machines and ask everyone to run the virtual machines. And that's also a solution. So what is the difference from a container and the virtual machines? And the big difference is how much you kind of virtualize. Yes, how much you virtualize actually. So in the virtual machines, you will also virtualize the kernel. So in a way, you are doing some kind of hardware virtualizations. And therefore, you are doing a lot more computations. So that has advantages, which means it's much more flexible. You can run virtual machines on Mac, not recently, but you can run the virtual machines on Windows, which runs Linux and stuff like that. That's very flexible. The issue is that it requires a lot of resource. And that means because you're virtualizing a lot. Container, actually, you are reusing the kernel. So you are only virtualizing the software in a way, and therefore you are reusing the kernel so that you are extremely efficient. And that's a good point, of course, for HPC. It's a good point also to kind of to separate single apps so that we have single app that's runs very efficiently in a kind of well-defined way. The issue, obviously, is that it's not multi-OS. So for Singularity, for example, you cannot run on Mac, you cannot run on Windows. Everything should be on Linux in this case. So that is more constraint of Singularity in that case, more constraint of container, that it's not multi-OS because you are reusing the kernel. So in terms of performance, as I said, the fact that you are using a container and not a virtual machines allow you to have what they call native performance. Of course, native, what they mean by that is that you basically run at the same speed as if you are not using a Singularity at all, which is obviously a lie. There's obviously an overhead, and there's no way around that. But what you need to understand is that this overhead is negligible / acceptable. So a couple of percent, 1–2%, so not that big. There's actually another cost that you need to be aware, and you need to be very careful if you need to have really full speed of your code, is that you cannot have full performance and portability. And you need to make a choice here between speed or portability. What I mean by that is that when you compile your code, you can compile, of course, with -0, and that means quite low level. -0 is for optimizations, it's 0.1, so it's relatively a low level of optimizations. Or you can ask to really take the maximum performance on your hardware, and then you typically go to -0.3. If you do that, you're going to use extremely specific commands for your CPU. And that means your code will be tailored completely for a given CPU or future generations, but will not work on extremely old CPU anymore, or at least older CPU than the one you are actually using to compile. So this is an example. So in this case, there is two types of CPU. One is Sandy Bridge, and one is Haswell. Both are quite old those days. That's for the example. And in terms of type of instructions, they can have inside what is AVX and what is AVX2. It doesn't matter if you don't know what it is, but it's basically some kind of specific instructions that speed up the computations. So what you can do is, of course, take, in this case, it's FFTW, which is one program I have no clue what it is about, and run one of the simple benchmark on it. You can compile it with actually -03, so the most higher level of compilations on this semi-bridge, and you will see that your code runs in a bit more than 1 minute. I guess it's 62 seconds, but I can only read a bit more than 1 minute. So now you have your code. Actually, it's done with Singularity, so it's portable, and you can run the exact same container with the exact same instructions compiled for the Sandy bridge, and you can run it on your new machines when that one is out, which is of course the case now. You can run on this as well, and you will see that simply because you are using a more recent CPU, you basically get a factor of 2 speed out without having to do anything. So you are reusing the exact same code, the exact same container in this case, and you get a bit more than 30 seconds now, so much faster code. But however, if you were targeting directly the as well, so if you were saying, I want to have the maximum speed on the as well, what you need to do is to recompile your code for the as well. And in that case, if you recompile your code and create a new image, a Singularity image for the as well, you can see that you actually can gain another 60%. So the fact that you have a code with Singularity that actually was compiled on Sandy Bridge, but can also work on was compiled on Sandy Bridge, but can also work on as well, make the fact that you are running on as well as actually a performance loss. In this case, around 60%. The fact that you could have a code that's running at 20 seconds, more than less than 20 seconds, but you actually have a code running at 30 seconds. So there is a choice really here. You decide basically which is the oldest type of CPU you want to target. And based on that, of course, the newer generations of CPU, you will see a decrease in performance in a way compared to what it could have been if you have recompiled. Of course, we have solutions for that. You can also say, I'm not going to compile only for Sandy Bridge, but I'm going to compile for different type of CPUs so that it can cover and if performance with using fat binaries that Mac people are doing quite well those days, what they call universal binaries, but it's the same. It's basically one code with more than one binary, and so that you can select at runtime which one is the most appropriate for your machine. That is very important to remember. Yes, they claim native performance, but the fact that you want, of course, portability means you have a trade-off implicit there. So this is true for the CPU. So that means if you really want portability, you need to have generic compilations. That means loss in performance. The same is true for GPU. But the fact that if you want to target only the most recent GPU, you can put compilation flag much higher and therefore have better performance. Also, if you want portability, you basically need to decrease a bit your compiling flags, actually. Singularity is handling, I would say, very well the GPU. What I mean by that is that it's very simple to link actually to the GPU library, and I will do an example at the end of the talk. But that's something on which you want to optimize. So there's the questions. Say you compile some software with -03 in the post part of your Singularity recipe. Will this target the host CPU architecture at container build time and potentially get into non-portable binaries? Or will Singularity intercept and expose the generic hardware for the compiler? No. I never test that, to be honest, but I never seen that Singularity is going to intercept that. So no, it will show the hardware that you currently have, as far as I know, and therefore, yes, you have the risk to have a non-portable binary. Yes, yes. -03 triggers some vectorizations, which is machine dependent, actually, as far as I know, Damien. Okay. So MPI, yes. So I say in terms of hardware, you need to think about the CPU and a compilation for CPU. The GPU is basically the same as the compute capabilities, and also interconnect MPI, which is also something very specific, of course, to HPC. And here the situations is not that great, to be honest. We'll see that a bit later, because portability here is extremely difficult to get. It's not impossible, but as soon as you try to use MPI, let's say in a non-trivial way, let's say, you will very quickly face issue with non-compatible version and stuff like that. So portability and MPI is in a situation which is far from perfect. The information has been reported to the Singularity author, actually to the Apptainer author. We'll see if that's going to improve. It's part of the documentations, but in practice, okay. We'll see if that's improve, I would say, in the future. So how to build an image? And that's the real starting point. So you have, typically you start from a container, or you start from what we call a recipe file. What I mean by that is that either you take a container, which is already a Singularity container, but you can also start from a Docker container. So you can actually convert Docker container to Singularity. That's typically easy to do. The issue is that for some of those commands, you need to be root. So you need to be sudo, and then you need to do Singularity build. And that's typically an issue, of course, for web depend when you run. You need to be root, actually not always, which is sometimes I found that I forget with the sudo, it's always work, but in principle, as soon as you use a Singularity file, typically you need to be root. I've seen some counterexample, I'm not sure why, but in principle, this root is supposed most of the time, at least, you need to be root. You have two types of output with Singularity. One is what we call the Singularity integrity file. So that's basically one file which is completely read-only, which is also signed, so it's secure. And that's the normal, let's say, default output of Singularity. And there's a second output where you don't need to be root, actually, which is called the sandbox. So there it will expose completely the full directory. So it's actually a real directory on which you do cd, ls, you can edit the file. So it's also writable. There's not that much reason to do that, sometimes for debugging, I guess, or for, if you want to make some tests and if you are not sure what you need to do in order to reach your goal, that's the way to use sometimes. So let's do a first demonstration, actually. So here I'm running on the virtual machines on some OpenStack, actually. So I'm actually in Switzerland, so I'm in CERN here. And here this shell is actually on the HPC cluster local here on the Metro 3. So what I'm going to do, I don't have my, no, I don't. If I'm doing that. Okay, don't see it, but okay. So I'm first going to, I need to remove it. First, I'm going just to pull actually an image from the cloud. So that library 2 is actually the syslab cloud, where and I'm putting myself also a lot of image, let's say. So if I'm going look here, I have this .cif, which is really this Singularity integrity file. And now it's actually unexecutable, so I can run it. And it's running exactly like if it's a local stuff. I can also run inside. So if I'm doing Singularity, I will do exec, the name of the container I want to do. And I can here run some commands. So the first commands I'm going to run is who am I? And we see that inside the Singularity container, so that's a command which is run within the container, I'm actually myself. So if I'm doing outside the container, who am I? I'm also Almatel. So I'm actually the same user within the container and outside the container. The second thing I can do, is to check which OS I am. And I can see here that I'm actually within the container running an Ubuntu versions, actually Ubuntu 20. And I can run the same command outside of the container, so directly in my shell. And you can see here that I'm in CentOS. So you can really see that actually I'm not running the same OS. I can therefore run different commands, but I am the same person. So this, you should see them as two different systems, but you can see that it's actually the same person in both. The next big stuff is you can do ls. And if you can do ls outside and within the container, you can see also that's the same file. So you can see that actually you are working on the same file, both inside and outside of the container. So it's exactly the same local directory. And I can even create some file from the container. So if I'm doing touch hello, which doesn't exist yet, and now doing ls outside of the container, you see that now I have a file hello, which of course doesn't contain anything. So it's actually kind of, I mean, it's actually the same file system. And if I'm doing ls minus, oh, I don't need that much, but okay. You see that actually this file was created, and that indeed I am the owner of the file with the normal permissions and stuff like that. So this is very practical way because you can interact with the file system inside and outside the container in the same way, and therefore that's very, very practical. So the big issue, obviously, is that you need to be root in order to create. So here, usually the pool. I could have done also the build. So that is basically converting or recreating an image. Actually, I'm going to do it. Let me copy the comment. And then I need my password here because it's root. I'm on a virtual machine, so I'm actually root on that machines. And I can override. But that really means I need to be root on the machine. So that's why I'm using here a virtual machine on OpenStack, simply because I need to be root on the machines. And that's something, of course, you cannot do on the clusters because you are not root on the clusters. So there is a solution actually for the clusters. It will take a bit of time here. I will not wait. There's an option which is the remote build. So that is the features that they are removing actually for Apptainer, which I'm a bit sad about it, because I think it's a wonderful features and it's very practical features of Singularity. So in Apptainer, there is something that they're going to be removed for very good reason in a way. It's simply because it's a private API, and therefore it's not something that other company can link on it. So it makes sense for Apptainer because it's in the Linux Foundation. But at the same time, these features is for me one of the greatest features in a way of Singularity, is the fact that from basically any machine which has Singularity, you can use this -- remote and you can run your commands. So I'm going to do that from the method tree. So here I'm my normal user. I don't even need root access for this account. I'm just doing Singularity build without the sudo, but with this -- remote, and therefore it's going actually not to run the creations of the image locally on the clusters, but it's actually going to do it on the cloud from the syslab cloud. Very practical, very easy way, in a way to run your command. So of course, in order to do that, the first thing you need to do is to create an account on the cloud, and then you need to identify yourself via a token. But if you go on the cloud, it's very simple to do. Then you do Singularity remote login, you copy your key, and that's it. And after that, you can add the -- remote. Obviously, it also makes sense to force that all your build with the remote, and therefore you can use the environment variables for doing that. So obviously, you may want something more reproducible in a way than using, for the moment, the only example I've done is to use previous executable, previous container, sorry. What you may want to do is to basically build a file so that you also explicitly make how to build your code. So that's a very simple recipe file, which contains, so that's the most basic one in a way, which contains 3 parts. The first one is your starting point. So you typically start from another container. In this case, it's a Singularity container. You can also start, obviously, from a Docker container, actually. Then the run script is what is going to be executed when you run the container. That's typically the executables that you want to do. And then finally, the post is, it's a bit weird to call it post, to be honest, but okay. It's how you install the applications within the container. And obviously, as I said, you need this root to be running. And I'm going to do an example. So yes, I'm calling it Ubuntu. Yes, so in this example, I make it relatively simple. I'm starting from Ubuntu 20. What I want to do is basically install Python 3 on any machines with this container. So when I run the container, I'm just starting a shell for Python 3. And how to install it, since it's Ubuntu, it's apt update, and then installing Python 3. As simple as that. I've add another block for the help. With the help. Okay, so there's a question. So what if the Singularity image is built on a remote machines and the remote machine has different architectures than the one where Singularity applications will later be executed? Is there a risk to its a performance loss in this case, compiling code infrastructure? Yes. So yes, compiling, yes, exactly what I explained before actually. So yes, if your architecture is older and depending on your compilation flag, you might have a loss in performance. Or you might have not code not running at all. If it's newer, you can have a loss of performance. So yes, that's obviously the issue of portability, that depending on how much you optimize your code, you can have issue, yes. So now let me run that. So here I need to do sudo. Build, and put the name, which I will call Python 3, and then the name of the file. And I need to pass my password. And now it's going to start to build. It's Python, so it doesn't take too much time, but that's fine. Okay, I will not continue to look at it. So in the recipe file, you can have more options, obviously. So this is the same as before. The setup, it's quite interesting, especially in the case of remote build. So that's how you basically, it's a set of commands that you run on the host. And that's why you can do some wget to get some information to have the initialization files ready on your host, actually. Yeah, that's basically some wget. Then you can say how to copy files from your host to your container, and that's the files part. You can set up some environment. This is where we discuss is how you install your code. That's when you run your code. Some labels, which is obviously useful to put information, who had done the code, what is your email, what is the versions of the container, and so on and so on. Okay, one thing which is very useful is to inspect the code of someone else. And let's do that. So you see that now I mean, I can go for this one. So now I can run Python 3. See if you see that it's open Python 3 terminal. Okay. And what I want to show, it's Singularity inspect the file, and I will take the one I'm taking online. So yes, so with this Singularity inspect, you can really see what's going on in the basic build of also other people. So in this case, I was taking this image from online, actually, so I can take a look what they do. You see they put some environment, that's the run script that they run. Date cow say a lolcat, so date is printing the date. Cow says make an image of a cow, and lolcat, if I'm correct, is putting some color. And you can see here basically how they do the installations, which is basically some apt-get, in this case, something relatively easy, but you can see here how they target different type of architecture. So just to reminder what's the output of it, it's, I'm running it, go latest, you will see that indeed you see a go, the current date, and with different color. If I'm correct, the color actually change each time. It's a stupid example, obviously. Okay. No, one button. So you can work, of course, with your image. One command I don't think I've made example yet is Singularity exec. No, I did actually. So you can actually execute command. What is really nice, and I will do the demonstrations, is, as I said, the file system is the same, of kind of the same at least, within the container and outside the container. So therefore, if you pipe in here, so this command, Singularity exec, so that's the name of the container, then you run cow say, and I'm a cow, that's what's the output normally, but you pipe it to content. So with this command, actually, it's not fully clear, at least it's not fully clear to me, if the piping of this command is going to occur on the virtual machines, within the container or outside the container. It's kind of not clear to me where it's happening. At the end of the day, it doesn't matter because both file system is the same, and therefore shell piping are completely working normally, and there's no issue that your file will arrive here. So that's, as I said, you can touch file within the container and they will appear normally in the file system because the file system is really the one of the host. So that's very practical and you don't have issue. You can really write as yourself. So I already kind of make demonstrations. I don't think I need to do this one. Something I really demonstrate at least is that images are executables. So of course, that's not the case for the sandbox because in itself it's a directory, but you can directly run the image. You have the run script part of the definition that we've seen before, where you can basically run whatever you want. It's a shell script, so you can pass arguments on top of that. And okay, nothing too much to say here. To come back on the topic of the file system, so as you've seen, the local directory, so the one from which you run, is the same within the container and outside the container. And a lot of what we call special directory are also automatically mounted for you, and therefore you have access to the same within and outside the container. So this includes your home directory, the /tmp. So if you write by default in something in /tmp, this will arrive on the /tmp of your system. So in particular, if they put the /tmp on RAM, and therefore it has quite good performance, that is going to happen as well. You can use /proc, /sys, and /dev. So if you want to have random number, you can use /random and or urandom, depending on your applications. And those are the one of the system. So you can use those when needed and when appropriate, obviously. So obviously, you will not fit all your need with those special directory. So if you need more, you need basically to specify what is the mount point within the container and outside the container. So that's typically useful on clusters. For example, in CC, we have a file system which is shared between the different universities, which include the CC home, but it's also /CC in general. And therefore, you can specify basically how to access that with this -- bind options. So this can also be used for local scratch. This can be used if you have a /data where you put a lot of data on your system. That's basically how you kind of customize your access. So you basically tell your system, oh, I need to have inside my container, everything, let's say in /mnt. but on different systems, when you run your container, you can put your data in different positions, and then you specify that by the minus bind, and specify like that. So I'm not going to do a demonstrations now on the virtual machine, simply because I don't have a good example to use there. I'm sorry, but you will see in a couple of minutes, I have an example on the method tree to how to use the interconnect and actually use MPI. And I will see at that time, I will need to specify the binding path for the local scratch. And therefore, you will see an example on that. So as usual, every options of Singularity actually that you can pass via argument, like this one minus bind, then this is the mounting point outside of the container, that will be the mounting point within the container. This is something that you can also put via environment variables, so that you can basically have everything set up and you don't have to write all those arguments, obviously. Like exactly what's the same for the remote. Okay, one thing which can be useful is, of course, to share your image. That's something which can be quite practical, especially if you have base image that can be used by other people. So you have your basic, let's say, installations of your program, and you want people to start that to include their own resource in a way. So that's a nice way to share. And for that, the first thing you need to do is, of course, to sign your image so that it's secure. Singularity is relatively well done. It will create the open PGP keys if needed. If it's not yet there, you pass your information and that's it. So very simple way to do. And then after that, you can share it online. So you have, with the free account, at least a bit more than 10 gigabytes of space where you can put basically your image. So that you can use that. One thing which is weird is that I don't find, because someone asked me recently, I don't find any way to increase that limit. So looks like they don't have a button or something like that. But they are updating the website, so maybe this will arrive. So there's a questions. It seems that Singularity shell source your .bashrc, which makes sense, which I guess, can this be prevented, preventing alias definitions on hosts from being inherited from by the container shell? I would say you should try to avoid, in principle, Singularity shell as much as possible, and prefer basically in that case to use multiple apps if you want to use some stuff there. But I guess, I don't know, to that answer, I don't know. You should check the documentation. That's the only thing I can tell. I can check after the documentations if there's something specific there. Or maybe do Singularity shell minus help, but I'm sorry, I don't know the answer to that. It's certainly possible, but I don't know. And then you can push it. The path is a bit weird. You have your login. Then the collections is a group of stuff that you release, and then the actual file. If I'm going, for example, if I'm going to mine, if I can copy the link. Yeah. So this is my cloud, and you see that I have three type of release: some test, some one which are related to Python, which is kind of the example I showed you before. Actually, in this case, one which are useful for later, which is collections actually for MPI, where I have different versions of MPI, MPI 3. And you should have MPI 2 and MPI 1 as well, so that you can have a starting, and you will see that later, starting image for running MPI on clusters. Okay.
And then, as I've seen before, you can use Singularity pool to simply take that image and put it locally on your cluster. And you can also run them directly if you want, not that useful in a way. So, as I said, there are two main, three types of hardware that we need to be aware when we are using Singularity. The CPU, where we already discussed, I guess more than enough, the compilation flag issue and the fact that if you optimize too much, it might not run on old CPU. And if you not optimize enough, then of course you will have loss of performance. The two other hardware is MPI, so the interconnect, and the GPU. So what is the issue with MPI? I said before that I don't think it's work well enough. And the main issue is maybe something that Singularity cannot really help on, and that we might need a broader community to fix. But the main issue is that MPI is really related to the machines in a way, and it's also related to Slurm. So typically Slurm and MPI have strong connections. So you compile MPI for Slurm, and therefore, in order to have everything working, you actually need to have kind of a puzzle piece. You need everything that needs to be at least compatible. What I mean by that is that the versions of Slurm and MPI outside of the container and within the container need to be all of them compatible. And the main issue here, and I guess that's not the real fault of Singularity, is that sometimes for at least OpenMPI, this compatibility it's not only, I would say, the big versions. So it's not only, oh, you need to have MPI 2 outside and inside the container. Sometimes you need 2.1.1 inside the container and 2.1.1 inside and outside the container, but exactly up to this third number, so to the bug fixing release, to have everything working. So that's, of course, depends a bit of the features that you need on MPI. But if you need extremely advanced one, then you really need the exact same versions. For more basic features, the big version should be enough. But yes, that's a bit the issue, is that the compatibility layer there is sometimes extremely sensitive, and that you really need to have the same version of Slurm and OpenMPI inside your container. So there are officially two ways to link, to use Singularity with MPI, so an interconnect support. The one where we propose on our HPC infrastructures, or in general, the one I recommend, and the one I'm exclusively make it working at least, is this one. So basically, what we provide to you, at least in our consortium, but in some sense you can use it for the consortium if needed, or you can do it yourself or ask your system manager, is to start from a container where we have already installed the correct version of Slurm and the correct versions of MPI associated to it. So that is, in this case, this bootstrap, and I'm using my repo on syslab to basically provide you a starting example, in a way, a starting container, which only contains basically the MPI versions and Slurm compatible, so that you have exactly the same as in the clusters. And then based on that, you can basically add your applications. You can compile your applications with those, and such that you can continue and you know that you will have a final container which is compatible at least with our clusters of the OpenMPI within and outside. The portability is, as I said, not that easy to do. So let me do an example. So let's move to the terminal. And now I'm going to back to the method 3. And I should have an image here. Double checking my keynote what was the correct one. Is test MPI. I'm going to copy the line actually. Okay, it's already queued. So I'm going to srun here, my Singularity container, doing Singularity run. You see this ---- bind that I was saying before to link to the local scratch,
and then running my executable with on fork actually. And those are just to use my reservations so that I know that I have access. I don't have to wait, basically. And you see that it works perfectly well. So if I'm doing Singularity inspect this image, okay, minus less. And so if you look at how I've created this example, so I'm starting really from the container that I've designed actually for these clusters with MPI3, linking the file, moving a file, actually a test with just an hello world. And then what I'm running is actually my hello world. And I'm compiling it simply using the MPI version which is provided by this container. So that's one way that you can use on HPC infrastructures. We have that available for all the CLC consortium. I'm pretty sure that you can have similar stuff for VSC or whatever. But that's the main idea. You basically need to compile everything in a way, but that's fine. Another solutions, official solutions, is what they call this bind method. I didn't investigate too much, to be honest, but I failed to make it work on Llama 3 in less than 15 minutes. So I didn't investigate it too much. So I don't have a running example. But the idea is basically you compile your executables, you move only the binary within the container. So you don't have any library of MPI or Slurm within the container itself. And the idea is to link the host library on the flight with this --bind method again that you can see here, and the special export LD library path, so that you link your executables to the library of the system. That in principle is a bit more portable, obviously, but you still have the issue that you have compiled your code for given versions of the library, so you're actually not sure how much compatibilities with other versions of the library. So that in principle should work. I guess what I'm missing in this example is actually to also update the LD library path for Slurm, but I didn't test it too much because the other example is working very well. But I just wanted to mention that this is also solutions. I think quite a lot of people actually are using solutions. I'm pretty sure that by investigating a bit more, I would be able to set up that and make it work as well. So the other type of, let's say, important resource, obviously you might use is GPU. So here I'm going to do the example. You will see here a big difference compared from interconnect and GPU is the fact that in this case, you need to have additional flag. So you do Singularity run --NV, which is for NVIDIA, obviously. And that tells Singularity to basically connect with NVIDIA and to do all the magics in a way to find the library, to link to the library, and so on and so on. So in that case, I guess it's mainly NVIDIA which has done most of the work in the sense by providing all the API needed to make that possible. And that's probably what is kind of missing on the interconnect directions, I would say. So let's do an example. So for that, I don't need the method tree anymore, and I need to go to another clusters. Yeah, that will be better. Which are some GPU. I don't have reservations here. Which I already have pulled, which is a default TensorFlow example. So I have this. I'm doing LS. I have this. Oops, sorry. I have this Singularity image, which is just one of the default Singularity image actually. So now I can to check one thing. I can execute it. Yes, Singularity run. So in this case, I need to do this minus NV, and then the name of the Singularity image. And I can check here. So now I can do Python import TensorFlow. And I will double check the command to print because I don't know it. How to print the device to show you that I've indeed connected to the GPU. And then the next one. Let me copy the line. Here, and you can see that indeed it has one CPU, and now it should have the GPU somewhere, maybe above. I don't see it, but normally it's connected to the GPU. Yeah, no, I don't see it. Oh, it has some CUDA driver error, so that's weird. But it has linked to libCUDA at least, but I don't see the name GPU. It sounds weird. Yeah, I'm not 100% sure it at work. I guess it has, but I'm not fully sure. Maybe, yeah, I'm not sure. I'm not fully sure that I can, at least I will not be able to convince you that it does work because I'm not convinced myself. So, but in general, this minus NV works very, very well. I would need to check if it actually is able to connect here on the GPU, but I guess it has. At least it's connected to some library of CUDA. So you can see that there's some stuff, but there's also some warning that I would need maybe to investigate a bit more. So this brings me to my conclusions. So Singularity and Container in general are, I think, a nice way to share your code with colleagues. And therefore, if portable code that can run in multiple places, and therefore increase the way to reproducibility. Of course, there is a cost in terms of performance that even if Singularity itself doesn't penalize you, the fact that you need to have portable code will have some cost. The number of commands to learn, I didn't really make a demonstrations and didn't go that slow to show you all the commands, but that's not that big. We basically have a couple of commands, but it's not too complicated. One big issue when you start at least is the need to be root. I would say that for that, Apptainer will make it more difficult in the futures, but basically either use some machine OpenStack when it's available for you, or basically using this minus remote, and that's very practical. And then I think one of the main stuff you can do is to test basically how much you can install your program on different type of OS, and how you can deploy them and avoid basically issues. Check if your code is still compatible with Ubuntu 16, Ubuntu 18, Ubuntu 20, and so on and so on. And at the same time, being able to test that on HPC clusters without having too many hardware dependence. If you have MPI, that will be not ideal, I would say, but otherwise it should work quite well.